This is the third part of a video about determining magnetic fields and forces due to a collection of currents. If you have not watched the first two parts of this series, I would encourage you to stop this video and go do those because this might be a bit confusing. Here's the original problem. We have two currents sitting at vertices of an equilateral triangle, and we found the magnetic field at the third vertex. Now what we've done is we've placed another current at that vertex, and we're asking ourselves, what is the magnetic force that is being experienced by this third current? So just as a point of clarification, the current is here. On the last video, I drew in this figure because it was a little hard to see how this current was oriented. So this is just something to remind you that this current is coming out of the page. The current shouldn't actually be here. It should be here. So my apologies for that. But what we have, I've copied over from the first part of the problem, the magnetic fields B1 and B2. Those are the fields that arise from the currents 1 and 2, which are situated at the other vertices of this triangle, which don't appear on this diagram. I've also copied over the geometry from the first part of the problem. Those are all these angles here, this 30 degrees, 60 degrees, 230 degrees, 60 and 30 here. Now, what I've done is I've placed on the diagram the forces acting on I3 due to the magnetic fields. And so I've tried to keep these color-coded. This is the force acting on I3 due to B1. So I've subscripted this F B13, F sub B13, which is F sub B is the magnetic force. 1,3 is going to mean the magnetic force acting from 1 on to 3. Sometimes people will subscript this the other way, acting on 3 from 1. This is my convention that I'm following here. From 1 on 3. So this is I3 receiving this force. And over here, this red vector here is the force F sub B23 is from the field here, B2, acting on I3 here. How did I get those? Well, the right-hand rule, and recalling that all the magnetic forces have to act at right angles to the field and the currents. So for this one, I'm going to use the right-hand rule for forces, which is to put my fingers in the direction of the current that's coming out of the page. It's going to be a little hard to orient my hand properly, but my fingers are coming out of the page, and then curl them into the direction of the field. So if my fingers are coming out of the page, I'm going to curl them into the B field, and then stick out my thumb. That's going to give me the direction of the force. And I know it's perpendicular because that's how magnetic forces work. So interestingly, in the first part of this problem, I got this field as being perpendicular to this side. Now that I'm looking for the force, if I then require the force to be perpendicular to the field, the force has to lie along the line that's the side of the triangle. I found in the first part that the field is perpendicular to this side of the triangle. Now I'm finding that the force has to be perpendicular to the field, so it has to lie along this line. And for B1, it lies coming down and to the left. For B2, same idea. I'm going to put my fingers into the direction of the current, which is coming out of the page, curl them in the direction of the field. Again, it's hard to see, my hand's in a strange position. Stick out my thumb, I get a force acting up. It again is going to be along this line, right? This has to be perpendicular to the field. So, but in this case, it's going to be up and to the left. So I've indicated the perpendicularity here and here. All right, now that I have the force components, not the force components, the forces, I need to resolve them into components and add them vectorially. I'm not going to do just the forces though. As we saw in the second video, I'm going to deal with the forces per unit length. That is detailed up here. See the second videos for details about that. I've added onto this what B1 and B2 are, because when I go back and I plug in the magnetic fields to this equation, I'm going to need to know what those are, B1 and B2. So this is just the formula for the magnitude of a magnetic field due to a long straight wire at a distance d away from the source. So B1, sorry, this should say I1. No. yeah, this should say I1. That's the current one. So B1 arises from I1, which is at a distance D away from this point. B2 arises from I2, which is also at a distance D away from this point. Distance D because that's the side of the equilateral triangle. All right, going through the algebra a little bit. To get the force per unit length, I'm going to need to take the force, which is this, and divide it by the length, which will give me something similar to this. So how I've chosen to notate that is put a 1 over L outside of the parentheses to get the force per unit length, and then I just peel off the components. So how do I peel off these components? Well, we already had that this is 60 degrees and this is 30 degrees. We got that. Now, when we already had that this is 30 degrees, and we know that this is a right angle. So if I add these up, 30 plus 90 is 120, plus 30 is 150. To make 180, that means this angle has to be 30. So it's just a little simple geometry there. Once I get that this angle is 30 degrees, I can tell that this vector, FB23, makes an angle of 60 degrees with the horizontal. Similarly, I've already figured out that FB13 makes an angle of 60 degrees with the horizontal. So I've reminded myself over here what the cosine of 60 degrees is, 1/2. The sine of 60 degrees, root 3 over 2. It's going to come in handy when I simplify this. And now it's just a matter of slogging through the algebra, peeling off the components. In the x direction, I've got minus FB23 cosine 60, that's this component here from the red vector. And minus FB13 cosine 60, that's this component here. In the y direction, I've got positive FB23 sine of 60, that's this component here. And negative FB13 sine of 60, that's this component here. Once I plug in the cosine and sine, I get this expression. I get with the 1/2. And then this is actually FB23. So how did I get that? I took this expression, I3 times the magnetic field, and plugged in the actual magnetic fields. So what that looks like is minus mu naught L I2 I3 over 2 pi d. And then the cosine of 60 gives me 1/2. Minus mu naught L I1 I3 over 2 pi d. Cosine 60 is 1/2. Okay? Then this L that I've already put here to indicate that this is the force per unit length will cancel with the L's here naturally. The rest is just factoring in algebra. I'm going to do that again in the y direction. I would encourage you to work through that on your own. You have a solution in front of you. I'd encourage you to pause the video and work through it. If we get to the final product, what we get is this expression here. Mu naught I3 over 2 pi d times this expression in the radical, I1 squared plus I2 squared minus I1 I2. And then inverse tangent to find the angle. So that's all well and good. I want to show you, and notice we did that by looking at the forces individually and adding them vectorially. If all the way back over here, all the way back here, we had realized that we've already found this B field in the first part of the problem. I didn't want to go this route because I wanted you to see this step by step. But we did find this B field in the first part of the problem. And let me remind you what that result was. It's here. Mu naught over 2 pi d root I1 squared plus I2 squared minus I1 I2. All right. If I take that and I just plug that into this expression, I should get I3 times that expression, which is what I did here. This is the B field. I3 times the B field is going to get me this expression. And lo and behold, this is the exact same expression I got from doing it the long, hard way. So take that as a hint. If you've already done the hard work of finding the field, just multiply by the next current to get the force, or the force per unit length in this case.